So this is how it's known as, okay, pipe flow, or so if you have flow between two parallel plates and if it's driven by a pressure gradient, you call it a planar flow, with the name associated with him is Poisson, or circular Poisson flow. So what we have is a pipe, right, and fluid flow through it, and we found that Vz is given by r square divided by 4 mu into minus dp by dz into 1 minus r by r square. Is this right? Is this what we derived yesterday? So, we will analyze this equation a little bit. The first thing that we want to do would be to find out what is the maximum velocity. Can you find out what is the maximum velocity? Vz max minus dp by dz into r square divided by 4 mu, correct? The next thing that we want to calculate is the flow rate through the pipe. So, yes, volumetric flow rate, yes, volumetric flow rate. Q is equal to integral V dot dA, very good, okay. So, can you go ahead and do that? So, it is indeed Vz r dr d theta with r going from 0 to capital R and theta going from 0 to 2 pi. Is that obvious to everybody? Okay. So, can you go ahead and do that and tell me what you get? So, let us say P plus delta P is pressure here and P is the pressure here, and let us say L is the length of the pipe that you are looking at. Then you can replace dP by dz, in fact minus dP by dz is equal to delta P by L, because those are the quantities that you would know. Pi by mu upstairs, r to the power r square, is it? Some people are saying r to the power of 4, and I think I will go with that. Now, can you tell the rest? Minus dP by dz, so it is delta P divided by L. In fact, it should be 8 mu L. Is this right? I want V average. Shiva? Yeah. So, how do I calculate? So, I want to, so we find that the velocity profile is like that, right? It has a shape of a parabola, or actually it is a paraboloid because it is a 3D parabola. It is a paraboloid. With velocity being like that. Okay, the velocity is maximum at the center, and we also calculated the volumetric flow rate. It is also good to know what is the average flow rate. Yeah, so how do I calculate average flow rate? Yeah, so and what is integral dA in this case? Pi r square. So that is very easy. So you just need to divide by pi r square and you are going to get the V max, sorry, V average. Now I want to get Vz in terms of V max. Can you get Vz average in terms of V max? You understand what I am expecting from you? You have V max, you have V average. I would like to express V average in terms of maximum velocity. So, V average of course is r square delta P divided by 8 mu L. V max by 2 is V average. This expression V average, no, actually this expression Q is equal to pi r to the power 4 delta P divided by 8 mu L, or delta P is equal to 8 mu L Q divided by pi r to the power 4. Okay, this is one of the most used expressions. Okay, why is it one of the most used expressions? Because given a flow rate and pipe length and pipe radius, you will know which pump you should use to pump a fluid of viscosity mu. That is what that expression is giving you, therefore, it is used highly. Okay. What else? Yeah. So, when can we use this expression always? What was there in the calculation so far that told you that it need not vary linearly? In fact, we proved that it has to be linear because dP by dz came out to be a constant, correct? But you are right, in some cases, no, I think it is always linear whatever you do. The original assumptions, okay, that ur is equal to 0, u theta equal to 0. There can be situations where these things can develop, okay, and one of the simplest place where that can develop would be a turbulent flow. Okay, turbulent flow meaning flow is highly fluctuating, it will have all components. Okay, so there is a limit in which all our analysis is correct, and that is decided by the Reynolds number. When is a flow laminar in terms of Reynolds number in case of a pipe? You learned it? 1200 is it? Yeah, well, it's of the same order, I think it's close to 2000, 2100. So, when Reynolds number, okay, is typically less than 2100, that's when you get flow which you call laminar flow, right? So, below Reynolds number 2000, we have laminar flow, and that's when all this analysis apply. We need to know now how to do turbulent flow, which we will do later in the later part of the course. So whenever you use this expression, it is important to check whether Reynolds number is actually less than 2000 or 2100. If it comes out to be less than that, your analysis will be okay, you will be finding out the correct pressure drop, otherwise you should be changing your analysis. Okay. Let's do one more thing. Let's go back to our non-dimensional equation. What is the non-dimensional equation that we had, Rashdejit? Yeah. Can you tell me what is the non-dimensional expression we had? The corrected one, because I had made a mistake. Okay. What is that? 1 by? No. R square, capital R square, no, by mu u dP by dz is equal to
1 upon I star d by di star of I star.
Is this correct? So, now that we know what is u, what we had defined u as u max, right? So, can you substitute and find what that comes out to be? Suresh Kumar, what number comes out? You are doing it, okay. What do you get, Suresh Kumar? Oh, by the way, so we have a tutorial on Friday, right? So that tutorial will be held in MSB either 355 or 356 where the usual classes are held. I'll confirm the class room number and send an email, but that's on Friday at 11 o'clock, okay? So we'll do some problems there. 4. Okay. So in fact, so this is our what non-dimensional equation looks like, right? Okay, so this is very interesting because if you look at this, this is really the governing equation that told you what the velocity profile was, right? And this velocity profile has no information about the fluid properties, no information about the pipe dimensions. You see that? Okay, so that means this is like, whatever, pipe you take, as long as it's going to be a cylinder, whatever fluid you take, okay, if it's in the laminar regime, this is always going to be the governing equation. You're always going to get a parabolic shape, the parabolic shape with a maximum of, so what will be the value of uz star, maximum value of uz star? We defined uz star as uz divided by u, r star as r divided by capital R. uz star will vary between 0 and 1, r star will vary between 0 and 1. Okay, so the velocity profile is always going to be a parabola with a minimum value of 0, a maximum value of 1 in a space which will go from 0 to 1. Okay, as long as you non-dimensionalize that profile with these things. Okay, so that's what it says, irrespective of the fluid property and so on. You see the there is a minus, is it? Where is minus? Oh, it's a minus, is it? That's because of dp by dz. That can't be correct. So dp by dz should be, so the dp by dz, okay, will be actually negative in terms of value. Then only there will be a flow in that direction. So because you have higher pressure on this side, lower pressure on the other side. So as z increases, pressure should decrease. So dp by dz should be a negative quantity in terms of magnitude. Actually not magnitude, dp by dz should be a negative. That's why you always write it as minus dp by dz, so that the whole thing is a positive quantity. Yeah. That's the second derivative. Okay, I have gotten this 4, you can check your calculation, otherwise let's see. Okay.